Large signal and small signal analysis of MOS transistors. I will explain about the superposition theorem, how it is applicable only for linear circuits, definition of linearity, examples of linear and non-linear devices. Then I will talk about analysis of non-linear circuits using large signal and small signal analysis. Then large signal and small signal analysis of MOS transistor. Superposition theorem. This applies only to linear devices. What are linear devices? Device which follows the two principles, that is homogeneity and additivity. Suppose there is a function f of x where x is input, y equals to f of x where y is the output. Then if the input is a times x where a is a constant, then the output should be a times y. Additivity, if y equals to f of x, then f of x1 plus x2 should be equal to y1 plus y2, where y1 equals to f of x1 and y2 equals to f of x2. Here are some examples of linear devices. Resistors. Equation of resistor is V voltage equals to I times R. When the current I is multiplied by a constant A, then the output voltage V will be equals to A times I times R, which equals to A times VR. Hence homogeneity is passed. Similarly, additivity is also passed by resistors. For inductors, it passes the homogeneity and additivity rule. Capacitors also pass the homogeneity and the additivity rule. Examples of non-linear devices: diode, where the diode current equals to Is into e power ud by ut minus 1. So diode current is an exponential function of its voltage. The diode does not conform with the homogeneity rule, that is, when the input is multiplied by a constant, that is a times ud, the output is not a function equal to a times id. Hence this is a non-linear device. Any equation which has exponential term, square term, cube term are not non-linear. Example, y equals to e power x is non-linear, y equals to x square is non-linear, y is to x cube is non-linear, and so on. MOS transistor in linear region has the current equation ID, which equals to beta times UGS minus UTH minus half UDS into UDS. Here UTH is a function of USB, which is under a square root, and here ID is a function of UDS square. So this is a non-linear device because of the square term and the square root term. In saturation region, ID is a function of UGS square, so this is a non-linear equation. Hence a MOS transistor is a non-linear device. Example of a linear circuit. This is a circuit which contains only resistors with DC sources UDC1, UDC2 and AC source AC1. This is a linear circuit. For this we can apply superposition theorem. According to superposition theorem, U out can be calculated as follows. U out equals to function of UDC1, that is short the other two sources UDC2 and UAC1, find out the output voltage, plus short UDC1 and UAC1, find the output voltage, plus short UDC1 and UDC2 and find the output voltage, which is shown in this equation. This is superposition theorem. For nonlinear circuits, for example, if there is a diode, superposition theorem cannot be used. So we have to make the difference between the large signal and small signal analysis here. First step is perform the large signal analysis. So here we neglect all the AC sources. Here VAC1 is neglected and only DC sources are considered, that is UDC1 and UDC2 as shown here. UAC1 is shorted, UDC1 and UDC2 is considered. Using Thevenin's theorem, find out the equivalent Thevenin voltage and Thevenin's resistance as shown here. Thevenin voltage is UDC1 by 2 plus UDC2 by 2. Thevenin resistance is R by 2. Here R1 equals to R2 equals to R is considered. Now find the bias point using the equations below. Using Kirchhoff's voltage law, UDC1 by 2 plus UDC by 2 plus I times R by 2 plus UD equals to 0, and we know ID, current through the diode, equals to I0 e power q UD by KT minus 1. Insert UT in this equation and now you solve this equation to find UD and ID. These are the bias points of the diode. So now we found the bias point. This is the curve of the diode. We have the bias point UD0 and ID0. Now we perform the small signal analysis by using first order Taylor series approximation. Draw a tangent at the bias point. The slope of the tangent at the bias point, that is UD0 and ID0, is a linear one, and it is given by GD equals to delta ID by delta UD. So here we approximate the diode equation to a linear one where the current, small signal current ID equals to GD times UD. GD is the slope of the tangent drawn at the bias point. After drawing the tangent, the bias point is of no longer interest. Hence, we can move the origin to the bias point as shown below. Hence, in small signal analysis, DC voltage sources can be neglected, that is shorted. So here if you can see, at the bias point you can move the origin, and the DC or the bias point voltages are of no importance in the small signal analysis. Hence, in small signal analysis, short all the DC sources, that is UDC1 and UDC2. Keep the AC source, that is VAC1. Here VAC1 is assumed to be a small signal, that is its amplitude is very small. Replace the diode by its small signal model, that is this one, GD, current ID, and voltage across it is UD, which is given by ID into 1 by GD. So replacing it, we get VAC R2 GD R1. The voltage UD equals to U out equals to VAC1 times R1 parallel 1 by GD divided by R2 plus R1 parallel 1 by GD. The current ID equals to GD times U out equals to GD times UD. Now combining the large and small signal analysis, the current flowing through the diode ID equals to the ID0, that is the current obtained from large signal analysis, plus small ID, that is the current obtained from the small signal analysis. Large signal analysis and small signal analysis of MOS transistors. From the equation of the drain current in linear region and saturation region, we can say that ID is proportional to UDS square, proportional to UTH, which is which has a square root term on USB. Hence, in linear region, the drain current is nonlinear. In saturation region, the drain current has the UGS square term. So here as well, it is a nonlinear equation. So the MOS transistor is a nonlinear device. The drain current is a function of UGS, UDS and UPS. We need to perform large signal and small signal analysis. Step 1 is to perform the large signal analysis to find out the DC bias points, that is UGS, UDS, UPS and ID. Step 2 is at the bias point, draw a tangent and find the slope of the tangent, from which we obtain the small signal parameters, that is GM, which equals to dou ID by dou UGS, GDS, that is dou ID by dou UDS, which is nothing but the output conductance, GMB, that is dou ID by dou UBS, which is the transconductance due to UBS. These, that is GM, which is the transconductance due to UGS, GDS, GMB, are called the small signal parameters of the MOS transistors, which are obtained from the DC bias points. The equation for GM can be derived by differentiating the current equation with respect to UGS to obtain beta times UGS minus UTH, which equals to square root of 2 times beta times ID. GDS can be obtained by differentiating ID with respect to UDS, which when approximated gets lambda ID, where lambda is delta L by L and ID is the drain current. GMB equals to dou ID by dou UBS, which can be written as minus dou ID by dou UTH into dou UTH by dou USP. Minus time comes because of change from UBS to USB, which equals to GM times eta, where eta equals to 0.3 to 0.5. So the drain current, that is the small signal drain current, equals to GM times UGS plus GDS times UDS plus GMB times UBS. From this equation, we can obtain the small signal model of the MOS transistor, that is the drain current ID equals to GM times UGS current, which is represented by a constant current source, then the current GDS times UDS, which is obtained by a resistor, and the current GMB times UBS, which is represented by a constant current source. The small signal model of MOS transistor with parasitic capacitors, we know there is parasitic capacitance between gate to drain, is written as CGD, gate to source as CGS, then we have drain to bulk, that is CDB, source to bulk capacitance CSB, and gate to bulk capacitance CGB. And from the small signal model equation, we know that drain current ID equals to GM times UGS plus GDS times UDS plus GMB times UBS. So when source to bulk is shorted, generally the source to bulk is shorted so that we do not want the threshold voltage to be varying from this equation, that is this equation. So when we short the source to bulk voltage, that is when source is connected to the bulk, the capacitance CSB goes away, the term GMB times UBS goes away, and this results in the equivalent small signal model shown below, that is, we have gate to source capacitance, gate to drain capacitance, drain to source capacitance, and here the source and bulk is shorted, can write as S comma B, and the drain current ID is sum of GM times UGS plus GDS times UDS.